Today I am going to deliver pre-submission seminar on all the topic strategies for designing of reconfigurable FFT IFFT architecture for wireless communication system using Vedic algorithms under the supervision Dr. Laxman P, Professor Electronics Engineering Department, GHRCE. These are my registration details. I registered in 2012. Till now, I have delivered 8 seminars and published 7 papers. These are the contents of my presentation. Wireless communication plays a very significant role. WebDM it is used for multi-carrier modulation techniques. In this multi-carrier modulation techniques, FFT and IFFT are the important blocks that used for modulation and demodulation. The size of FFT and IFFT processor are varied application to applications. So in this, I observed that they are inefficient in terms of area, power, and speed. FFT and IFFT processor. So in this research work, what I have to propose the fundamentals of reconfigurable FFT processor to reduce the power, to enhance the speed, and to reduce again the area. This again the block diagram of WebDM transmitter. There will be all the IFFT used as the transmitter side and FFT as the receiver sides for modulation and demodulation. So in this I propose a reconfigurable FFT. So what I tried here, I have designed generalized FFT form. There we can select any type of FFT. So that is what the reconfigurable FFT. So motivation of this research work is to design in this FFT and IFFT processor. Then we have the signal, it is multiplied with Tudor factor. It is a complex multiplication. So that complex multiplier I have designed, and that I have used for FFT and IFFT processor. These are these problem statements. For conventional multiplier, there we have the storage elements are more, frequency is low, and area inefficient. So I have designed that complex Vedic multiplier to enhance the speed, to lower the power, and to reduce the size. Objectives: I have first designed conventional complex multiplier that I have compared with the conventional complex Vedic multiplier that I used for different studies in FFT, and that I have implemented in WebDM. These are the comments which I got till date in progress seminar. Literature survey. In our efforts, many papers they are found in like this first paper. The author has proposed pipeline architecture for fast Fourier transform. There, he has achieved the memory reduction, low power, and complex multiplication. But compared to my work, again that this paper, in this paper, the large area power consumption is more that I have found. The second paper, they have designed low power 64-point FFT architecture requires 25% multiplication and 36% addition, but again it is limited to 64 points. So likewise, I referred papers that I have summarized in table forms. There are transaction papers I refer. There I found that the working frequency in power consumption and area. So in some papers power consumption is less, so frequency is large. In some papers area is less, so power consumption is area is more, power consumption is more, frequency is small. So using this, in this paper, reconfigurable low floating point FFT architecture in 2013, frequency is 156 megahertz. It is low compared to the proposed research work. So what I have concluded here from this literature survey is that what area required is more, frequency is less, and the power consumption is also large. So I have to try to reduce these parameters. In this, I have designed a complex complex multiplier, which we named in FFT, FFT and FFT processor. So complex multiplier is the multiplication of complex numbers that the results is floating subtractor, floating adder with some 4 multipliers. This is the diagram, block diagram. How I have how I have implemented this multiplier. So for this, the base I have used Vedic mathematics. Vedic mathematics, it was invented by Bharati Krishna Tirtha ji, and all the sutras are recovered from the Vedas. So 16 sutras are there to perform mathematical operations. So from this, 14 number sutra, Urdhava Tiragvam, that is vertical and crosswise, that I have used, that we can use for any kind of multiplications. So here, what do you mean by this Urdhava Tiragvam? Here, this there you have the English name is vertical and crosswise. Vertical means straight above the multiplication, and crosswise means diagonal multiplication and taking their sum. So we can take from left to right or right to left. So this is the example 4-bit multiplication. So first we are taking in the pairing form. So first pair is vertical, second pair is vertical, first pair is vertical, second is crosswise and taking their sum, third pair is crosswise and vertical. Likewise we are taking. So in this case, compared to conventional one, the less multiplication and addition, there we have less number of multiplication and addition compared to the conventional multiplier that I use here. So this is in the form of again block diagram. How carry is added. This the first term is AND gate. Directly it is we are getting, but second is AND operation with this their sum. Carried is added to next stage. This carried is added to next stage. Likewise we are performing and calculating the results. So this is the that what first I have implemented for integer numbers only. So first 4 bits complex multiplier I have designed. There I got the results. I have taken the numbers 1 plus j15 into j15 plus j2. So there I got the results. So this results, this is about I have compared with the conventional one. Conventional one is both complex multiplier and this the proposed one Vedic for integer numbers. So hardware part is less, so that is area and power consumption is we can say less, and here delay again it is less. So speed we can say we are enhancing this speed. So this I have published in that I went to China to publish the paper. Next I have designed for generalized purpose n by n bit multiplication. So using this concept, now this how we can reduce n number into a small bit. So this is 8 bit. So 8 bit we are dividing into 4 parts. So again we are taking its vertical and crosswise. So likewise we are performing. So we can reduce that end point into a small points multiplication. So later means after this I designed 8 by 8 results I found, then 16 by 16, 32 by 32. Likewise again I have implemented FPGA implementation is done. So that also I published in paper. Next, this was for integer numbers. Next, I use their complex number, that is floating point numbers. There we have the plus, minus, and both integer and fraction parts. So for that, I use the standard IEEE standards. IEEE single precision format, single 32 bits. 23 bits is the fraction part. That is mantissa, exponent 8 bits, and 7 bits. Likewise, how I have converted into IEEE formats. It is given. This exponent mantissa and the number I have written in IEEE single precision format. Then how I have multiplied this using Vedic multiplier. So 2 numbers I have taken here. Mantissa I have multiplied using Vedic multiplier. Then it is again we have to write in normalized form, that is the process of IEEE 1 point some points, and then we are rounding that numbers because Mantis size 23 bits, so there is a need of rounding remaining bits we are truncating. Next exponent that what already when we are converting into IEEE format, so there we are normalized. So here is a need to again reverse denormalize. So I am denormalize using this 16:8 marks. So here inside that there we have 8 marks, 2:1, 2:1. There are 8 marks. So the signals, this MSB bits, that what the selection of this, it depends on what this MSB bit. MSB bit may be 1 or 0. So if MSB bit is 1, so it will select this A plus EB minus 126, and if MSB bit is 0, it will select, because then we have the combination maybe 0, 0, 0, 1, yeah, 1, 0, like this. So then we are exponent we are calculating, and the sign bit, again we know that 0, 0 and 1, 1, so we are getting there about 0, negative, negative, positive and positive, positive, multiplication is positive. So 1 we are using for negative and 0 we are using for a negative sign. If you are there 0 1 or 1 0, so we know XOR operation is 1. So there is the need to design 3-bit, 6-bit, 12-bit and 24 bits to multiply the complex number using IEEE single precision, because Mantissa is of 23 bits. So to get that 23 bits, so we are using 3 bit, 6 bit, 12 bit, 24. If you are taking 2, 4, 8, 16, 32, likewise we are getting. So we cannot use that multiplication. So for that I have designed this separate 3 bit odd number bit multiplication. So this is again 3 bits multiplication, its hardware parts, then the results which I got, then 3 bits I have used to design 6 bit. 3 bits pair, 3 bits pair, 3 bits again vertical, crosswise and vertical. So likewise we are design generalized form. So how we can design again a 6-bit Vedic multiplier, it is the hardware part, 3-bit multiplication, so 6-bit result, 3-bit I have considered. Next MSB, that what the MSB bits I have added with the 6-bit carry loop adder. Here that what crosswise and they are taking their sum, so there we are getting 6 bits, so there is a need of what 6-bit adder. So in this way we will get about 12-bit output, 6 bits Vedic multiplier. The results which I got. Next I designed using 6-bit, 12-bit, same process. Next I designed 24 bits using 12 bits, same vertical and crosswise, same hardware structure. Then exponent, how I have implemented exponent part, that is also given. Now results of floating multiplier, that I have taken any at random numbers, that may be negative into 0, positive into negative, negative into this positive, so which I have got here the results. Then some parameters I have considered here, that what the from synthesis reports I found. Then when we are multiplying the that two numbers, complex numbers, so there we have the need complex floating adder and floating subtractor. So this floating adder I have designed again using same IEEE single precision format. So these are the process again how I have converted into a IEEE format, that the resultant Mantissa. Its results. Then floating subtractor I have designed. These are the results that I have taken here. The numbers. This, if I convert this for this, I will use the Google calculator. I put there these values and I checked. So I found this the minus 1.414. That is this last one is the sign bit. Then complex using this the result total complex multiplier a minus a j b, yeah, minus C minus JD. So likewise I have performed this. So for these two results I got the results. So that I have compared with the this complex with the Vedic. So here I found frequency it is large and the some parameters hardware part it is reduced. So area and power consumption we can say it is reduced and frequency it is large in 207 megahertz. Then generalized reconfigurable FFT that have up to 1024 points reconfigurable pipeline FFT processor that I have designed. So using this here the Radix 60 inputs we are applying the complex multiplier which I designed that I have used here, and this sorting algorithm it is used to select any the number which FFT points which we want for our application. So these results are compared with the authors. So here also this for 1024 gives frequencies high compared to this the previous results. This is the utilization again the comparison for 512 point FFT. So utilization is less and the frequency is high. This I have designed 2.4 for various points I have tried. It's in graphical form. Then comparison various FFTs that I have compared with again the authors. So again that there I found using some techniques what they use, what I use. So frequency is 20 megahertz. Then I that what the FPGA implementation is done. So this is 2 point FPGA implementation, 4 point FFT implementation. Then I use Vertex 7 FPGA kit to implement this. So what I used there to check my result. I have applied 125 kilohertz input to signal from function generator to CRO using and that CRO is connected to targeted FPGA kit. Then after dumping, what I found here, we get 120 kilohertz output frequency peak on CRO. This on x-axis there are 10 divisions. Each division contains 5 subdivisions. The bandwidth is said to be 10 megahertz. Each of each division of 1 megahertz. It is divided into 5 parts. So subdivision is 200 200 kilohertz. So this between that half of this is what 125 kilohertz that I have found. Then I have implemented WebDAM modulator using this. So these are the synthesis reports. Then again the hardware parts, how I have that what the percentage wise calculated. And again that FPGA implementation for WebDAM that is also implemented using this Audacity software. So in this single frequency signal 64 kilohertz, it is generated through Audacity software present in the laptop. Laptop is connected directly to FPGA kit via mic. So that what this is the input signal and the output signal which I have observed using this. So conclusion from this, it is that what the conventional, if you are using conventional multiplier compared in applications, so there we need more area, large area, power consumption is more and the speed is less. So to that I have reduced using the Vedic multiplier. Features of maybe this we can apply, there we can use double precision format. Then the FFT points, again we can increase the FFT points. That we can apply for Memo WebDAM system also. I published papers in international conference in China. This paper I published in ISTEC Japan, and this paper I published in Mumbai at ICCCV at Thakare College of Engineering. And some papers are published in international journals as the main authors. This I have applied for patents, so this is in the process. And as a co-authors again published some papers. These are the references. Thank you.
Thank you. Multiplier.
This complex multiplier. This complex number.
Oh,
It's a complex number.
questions? Suggestions? Determined to be silent. For future, anything the design. Of course, you have used algorithm. I have no issue. That's good. And proved that things are there. Is there any way by which you can go further?
Forwards.
No, you have used the algorithm of Vedic.
Yes.
So you have achieved something. Conventional, addition,
Conventional is
multiplication. Can we take some example where these are involved?
This algorithm can be used.
Now you have established the algorithm with, let us say, typical numbers of addition and multiplication. Now I have a scenario where all these things are there, a system where the total time it takes conventional for this is so much. My Vedic mathematics, that will quantify.
Yes, miss.
Can you
Where we need the complex multiplier, then we can use like we just now madam told.
You have to take an example.
FR filter.
Not just two numbers adding, improved. I want. Next step.
That I was taking 1024 points and up to 32 into 32 bits.
Example.
Can we find the cube root of unity?
Cube root
of unity. Do you know 1 plus omega square is equal to?
Take one.
Using this.
Yes.
Sir.
Can you find the cube root of unity? What is the challenge in finding the cube root of unity? And how that will be done? Do you know?
Likewise, sutra, it is used for multiplication. Likewise, the many sutras are available, 16 sutras, that we can use for cube, we can use for square root to get the square root, we can use for again to get.
I want to find out a factorial of a big number.
Yes, get factorial.
There we can show.
Very correct.
Yeah, this.
Otherwise, can we use it for modeling of the frequency, complex frequency? Attenuation part and amplitude part. Complex frequency represented by complex number. Can I use this model for representation?
Yes, for factorization also we can use.
Anything, just one or two couple of examples of that practical nature.
Yes, we can use. So that
if you do, then it gets more value.
Yes, that we can
your thesis.
Yes, we can in future.
You don't take much time because you have already all the things. All that you have to do is input. And then doing convention, research.
Research can be appreciated. Some examples are added.
Always.